Hi everyone. Today's lesson will be about oscillations. So that will be the first lesson of oscillations, chapter 17 of OCR. We'll be looking at simple harmonic oscillations in more particular, but oscillations refer to anything that's moving back and forward from an equilibrium position. If you have a pendulum and you pull the bob away, it will oscillate from its equilibrium position. We have looked at so far a lot of different motions. So we looked at linear motions where we have objects traveling along a straight line. We looked at projectile motions, which we analyzed the direction of x and y motion. You have also looked at circular motion, so how things behave when they're moving in circular motion. And this will have a really strong link with what we will be learning actually on this topic. And we also looked at emotions in waves, in vibrations. So we looked at waves what we're going to see basically here is quite similar to what we've seen in circular motion and in waves in the AS content. So here are some key terms that will be useful that we already learned in waves. So you're expected to know what displacement, amplitude, period, frequency, angular frequency, and phase difference are in terms of oscillations. Angular frequency is different, even though it's similar, it's exactly the same equation as in circular motion. Instead of calling it angular velocity, we call it angular frequency. You also need to be able to define simple harmonic motion, and the definition is actually based on the equation. And you also should be able to talk about techniques and procedures used to determine frequency or period for simple harmonic oscillations. Also, you will need to be able to find the solutions to this equation. You don't need to know how to get the solution, but it's a useful thing that I will show. And you just need to be able to use the equations basically that will be given to you. So basically how to calculate the acceleration, the displacement, and the velocity at a particular point of an oscillation. You also need to be able to state that the period of a simple harmonic oscillator is independent of its amplitude. This is quite an important part, which we will talk about. And graphical methods to relate the changes in displacement, velocity, and acceleration with time, basically, in simple harmonic motion. We will also have a look at the energy of simple harmonic motion, so how there's an interchange between kinetic and potential energy if we assume there is no air resistance, hence no thermal energy losses, and the energy displacement graphs. So let's start with firstly the key terminology. So what we have is displacement. So I will let's focus actually on just one pendulum. So let's say I have a pendulum hanging from a fixed position. So this is the ball hanging at the bottom. This is the pivot where it will oscillate about. And if I pull this bob, I'm displacing the ball in one direction. That once I release it, so you don't push it with a force, you just release it, you displace it and release it. Once you release it, it will keep moving back and forward from its equilibrium position. What we considered as zero displacement. Now, if it moves in this direction, I want to take this direction as positive, then the displacement, let's say by the time the ball reaches here, will be a specific amount of displacement. So it's the distance from the equilibrium position. So that will be your x. And this is got a positive and a negative value, it's displacement. So it could be positive or negative. The symbol is x and the unit is meters. Amplitude is the maximum displacement that from the equilibrium position that the object will move from. So that will be the full displacement that it can get to. That's the amplitude. A capital A is the symbol for it, and the unit is meters. Just remember not to confuse amplitude with area, because we usually use A for area as well as a symbol, either cross-sectional area or surface area. So be very careful with that. Period is the time taken to complete one full oscillation. So, for example, in the case of a bob, for example, if you displace it to this position, then it's the time it takes to go to equilibrium, then pass to the other maximum displacement, the positive amplitude, return back to equilibrium, and then back to where it started. So that's one oscillation, one full oscillation, and it's measured in seconds, and the symbol is capital T, like a period of waves. Frequency is measured in hertz. The symbol is F, just like in waves, and it's just the number of complete oscillations per unit time. So if you had, for example, if you were doing an experiment and you counted, I don't know, 20 oscillations in 10 seconds, for example, then you can find the frequency by saying, okay, there were 20 oscillations in 10 seconds. That would be 2 oscillations per second, or otherwise 2 hertz. And then the last thing I wanted to come across for now, before we go on to the next term, is the phase difference. It's usually shown by the Greek letter phi. It's measured either in degrees or radians, and it stands for the difference in displacement between two oscillating objects. We have seen phase difference in waves, and that was the difference in displacement between particles along the same way, or different, or the particles along different waves. In the case of oscillations, is the difference between the displacement of two oscillating objects. So, for example, if I had two pendulums and they were both at maximum displacement at the same time, then we say that they are in phase. They have a 0 phase difference. If one of them was at maximum positive displacement while the other one was at maximum negative displacement, then we call this antiphase. Or what you would say that they are in, they have pi radians phase difference, for example. So we'll move on to the next bit. Okay, so what you see here is a ball. So we have a ball that's at equilibrium to begin with. So this is your ball here. Now, if you displace it, for example, to this point here, what you will expect is that that ball will keep oscillating back and forward from that position and in its equilibrium position constantly if there is no friction and no air resistance, because obviously those are resistive forces. They will cause, they will go against the motion of the object, and that will slow it down, which will eventually stop it from moving. So if we remove those factors, let's say we do this in a vacuum, then obviously you will expect the ball to keep oscillating constantly at the same amplitude the whole time. It will never stop. So what you see at the graph below, it's this graph here, is how the displacement of that ball varies with time. So it's easy from this graph, since we already know the displacement time motion of the ball, we can get the period of it. So that's displacement against time. So remember, the period can be taken, is quite similar to how we get a wavelength and period for waves. So you'll take it from one point of the wave to the same point on the next wave. So that will be your period. Your amplitude is always from the equilibrium position up to the maximum displacement that it can reach. Then that will be your amplitude. So always from 0 to that position. So what happens in circular motion? What you see, how is circular motion linked to simple harmonic motion or oscillations in general? By the way, for the purpose of this chapter, we're only looking at simple harmonic motion oscillations. Mostly is the reason is because it's much easier to analyze in terms of the mathematical analysis, and even though there's loads of different oscillations that could involve 2D or even 3D dimensions, we don't look at that as of the course. So we will only be focusing on one type of oscillation, which is the simple harmonic motion only. So, like I said already, we will link circular motion to simple harmonic motion, to oscillations, basically. So the way we do that is by looking at how an object will move around the circle, okay? Now, we know that this is an angle theta here between where the object is in its path. So even if the ball was here, for example, the angle would have been a bigger theta. But let's just focus on the one point here. Now, if the ball was initially at this position, and we'll only focus on the x-axis, by the way, we're only interested in the x-axis and what happens on that x-axis. So if the ball at time 0 was at its maximum displacement, or what it appears to be on this axis, on the x-axis as the maximum displacement from the center of the circle, then that would be your maximum amplitude, that would be A. And this is the point plotted here. Now, after after the object moves to this position here, so the new red ball that I drew there, we can take the part of it that's only aligned with the x-axis. So, for example, now this new point will be here from the 0 position. And we can figure out how the displacement of it varies with time as it rotates around the circle. So you know that if it's here next, then it will come up shorter in terms of the, it will come out a little bit shorter in terms of its x-axis position. So how do we do that? We use trigonometry. So you have your triangle. So I'm using just this triangle here to find basically this distance and express it in terms of what I do have. So that's your theta. This is the amplitude. Since this is the maximum amplitude here, we know that the radius at any point will be the amplitude, and we need this distance. Basically, we need to find what this is. So what we need is adjacent over hypotenuse. So that will be cos theta is x over a, because remember this is your a, your amplitude. That will mean that a is equal to, x is equal to a cos theta. So we know that the displacement as it moves around, the angle is changing, is dependent on a function, on the amplitude firstly, and on the function of cos theta. Now what you see here is a displacement starting at the maximum amplitude, and you see a cosine curve, but that cosine curve is a multiple of the amplitude. So that's how you know whether the pendulum starts from maximum positive displacement or maximum negative displacement, or even if it starts from its equilibrium position. So if you saw a graph that starts from 0, that will mean they use the sine function. So it will be like something like that. You get the point. Also, from circular motion, we said that the angular velocity is omega theta over t. Now, we're no longer going to call this as angular velocity in oscillations. We will be calling it as angular frequency. However, we know that the angular velocity is by how much angle is covered per unit time. So I can rewrite theta as omega t. So I can replace this theta with omega t. So x is equal to a cos omega. A cos omega t. So we just linked the displacement at any single point to the amplitude, to the wave function, and omega, the angular frequency and time. So we will be able to calculate. I will be coming back to this actually in a bit. But yeah, you are able to calculate the displacement of a pendulum or any object that's moving in oscillation, in a simple harmonic motion, at time t, basically. So if we know the time, if we know the frequency, and the amplitude, you can find the displacement of the oscillating object at a specific time that you're asked to calculate it for. So yeah, that's basically pretty much how we can link circular motion to simple harmonic motion. And the idea is that obviously as this is moving around, as a ball P is moving around the circular path, it does slow down when it comes closer to its maximum displacement, but it does speed up when it goes towards the center. And we're going to see how that works with the ball as well. So what you would expect from this ball is as soon as you release it from here, it will start speeding up towards the center. But then as it reaches the maximum, let's say if this is the positive displacement, if it reaches the maximum positive displacement, it reaches zero velocity. So it accelerates towards the center all the time, but it does slow down to zero when it reaches its amplitude, either the positive or the negative amplitude, either case. Okay, so this is the last definition that you do need to know. So for angular frequency is what we use to describe the motion of an oscillating object, and it's basically the equation that we have already seen in circular motion. So that's angular frequency, and this is a period, which is always in seconds, or frequency, which is always measured in hertz. Okay, so what is simple harmonic motion? Firstly, simple harmonic motion is one of the most common oscillating motions. So what you have is always an object that is oscillating from an equilibrium position, but simple harmonic motion has its own definition, and the definition is based on this equation. So it's easy to remember once you look at the equation what the definition actually is from it. Now, A stands for acceleration and is meters per second squared. Omega is the angular frequency. And you have X, which stands for displacement measured in meters. So it has a rads per second as well for the units. So now for an object, omega will be constant and X will be the displacement from the equilibrium position. There are two key features in this equation. One of them is the fact that since omega is a constant, acceleration is directly proportional to the displacement. So that's one of the parts of the definition. So in a simple harmonic motion, the acceleration of an object is directly proportional to the displacement from the midpoint. And the second point is that it has this minus sign, which means that it is the acceleration is always in opposite direction to the displacement, because it's always directed towards the midpoint. So that's the second point, sorry. The minus sign means acceleration is in opposite direction to its displacement. And we can see the example here. So if the bob is moving this direction, this is where your displacement will be. But acceleration is always towards the center. The same thing here. If the bob is moved this way, we know that the displacement is in this direction, but acceleration is always pointed towards the center, towards equilibrium, not center, sorry. So that's basically what the definition is. So that's the definition of simple harmonic motion. So if you're asked to define simple harmonic motion, I would suggest writing down the equation and explaining what each term means. So in terms of acceleration, it's directly proportional to the displacement, but also acceleration is always towards the equilibrium or the midpoint. So if I plot it using this equation, acceleration versus displacement, then you would expect to get a straight line that has a negative gradient, and also it should be passing through the midpoint since there is no plus c component, there is no y-intercept. To remind you that y is equal to mx plus c. So what we have here, your y-axis is your acceleration, your x-axis is the displacement, so that means your gradient should be minus omega squared. So wherever you get the gradient from, doesn't matter because it's going to be the same everywhere, but use the biggest triangle possible. So when you get the gradient, it will be omega squared. And if you want to find omega, then you square root the gradient. And you get the, and you can also calculate the frequency through that as well. Okay, so this is a very important part of simple harmonic motion, and is not very well explained in questions by students usually. So do put a little bit attention on this part. Is that in simple harmonic motion, the period of the oscillator is independent of its amplitude. This is called isochronous oscillation. Iso means the same, and chronos in Greek means time, so it's like same time, no matter what the amplitude is. So in other words, if I had a bob, an oscillator, say bob again, even if I displaced it at a bigger amplitude, it will still oscillate no matter what you do to it. It will still oscillate with the same amount of period, so it will take it the same amount of time to complete an oscillation, regardless of how much you pull it further away from its equilibrium position. The only thing that could change its period is by changing the length or the mass that you're hanging off it, which is something that you should be able to do as an experiment. So we have spoken about the displacement, amplitude, period, frequency, angular frequency, and phase difference. We talked about the angular frequency, what simple harmonic motion is and how to define it. I will have a brief talk through this part where how to determine the frequency of simple harmonic oscillations. We also showed where these equations come from, but we will look a little bit more in depth into it. We spoke about the period being independent of amplitude. This is a big star here because it's quite important. And we only looked at the displacement time graphs so far, so we will look at velocity and acceleration. So I will start first with the techniques and procedures and then move on. Okay, so one type of experiment that you could make is by using a mass on a spring. So if you pull the mass, it will make the spring oscillate back and down, up and down, sorry. And the best way to do usually these type of experiments is to use data loggers and sensors because they tend to be very precise in their measurements. The fact that we remove human error from timing, for example, for the period, is very, very useful because it makes our answers more precise by removing that human reaction time. In order to do the experiment, you will need a piece of string. Now, the reason that we use a piece of string is because when you do move the mass upwards, or when you let it go to start oscillating, it sometimes swings from side to side. So the string actually helps stop the mass from swinging side to side because that could affect your results. So that's one key thing, like the key things that you can do to avoid any mistakes in your experiment is to use a string for avoiding the swinging of the pendulum, of the mass on the spring. So you will set up with a string, a spring, and a hanging mass. Obviously, you need to record what mass you used, so that when you do the experiment, if you want to ever repeat it, you can make sure that the experiment is repeatable. to recollect the same values using the same exact measurements that you had to begin with, because the mass can affect the period of the oscillation. So if you're trying to calculate the frequency, for example, so this is to measure the frequency, but you need to be careful with what the actual objective is for the experiment. So for example, in this case, we want to measure the frequency, we have to keep the mass the same. But if we wanted to figure out how the mass affects the frequency, then obviously you will have to change the mass and then measure the frequency with the same steps that we will talk about. You definitely need a clamp stand, a clamp and a clamp stand to hold the string in place. You need a ruler that's fixed, so you can also make to take the first reading of how much you have moved the mass to begin with. So basically you will record your amplitude to make sure that the experiment is again repeatable. Always read the value from the ruler and make sure your eyes are leveled with the ruler, because otherwise if they're not level, then you can have parallax error. And to remind you that this is, for example, if this is the ruler, this is your eye, it should be aligned with the measurement. Let's say that's the measurement you needed to make. If you look at it from above or from below, it actually changes the viewing angle, which gets you the wrong answer. This is what we call parallax error. Just a little reminder there for what you already know. So yeah, you have your position sensor, so it measures the positions relative to the sensor and the time at each unit time that you choose, that you set up the computer basically, and then that feeds into a computer that can record continuously and plot a graph for you already. So you can even, by the way, you can do that normally as well. Now, the big tip I wanted to mention here is when you're taking a reading of the ruler to begin with. Now, it's really hard to align and figure out the initial position of the reading. So if this is the ruler and let's say this is the place where the mass is aligned with at the bottom, then you should make sure that something is aligning these values clearly, and you can do that by using a set square. So you can place a set square like this to make sure that this value is fully aligned with the value that you're taking a reading of. So a set square is basically to get an accurate reading for the initial displacement of the mass. And that's how you can get the clear reading. So that's another tip to remember to include in terms of getting accurate results. Yeah, so basically you will displace this mass, so you will lift it up, let's say here, and then you will let it go and it will start oscillating up and down. The data logger will get your readings completely, and make sure you let the experiment run for at least 10 oscillations. We usually prefer 20 if you're doing the readings on your own using a stopwatch, but 10 oscillations is enough. And then once you collected your data, you can use the computer to basically get a displacement time graph, just like the one that we saw already. Now, in an experiment like this, you will find that the amplitude of oscillation actually decreases with time. However, you're going to notice that the period and frequency don't change with time. And remember, that has to do with the fact that that period is independent of amplitude. Okay, so like I said before, you can use this exact same system to investigate how different variables can affect the time period of an oscillation, but make sure that you only change one variable at a time while keeping everything else fixed, and to repeat the experiment for each different value of independent variable you're investigating. So you could change the weight of the mass, you could change the stiffness of the spring that you're using, or you can even change the size of the initial displacement, which you know that you shouldn't get a change in the period anyway for that, but that's an investigation still. You will find that the heavier mass actually takes longer for a complete oscillation, so it has a bigger time period. The stiffer spring leads to a shorter time period, while, like I said, the initial displacement will have no effect on it whatsoever. Okay, so we can also have a quick look at the pendulum setup. I will spend a little bit less time on this. Okay, so a few things to notice. This is a in case you don't have a sensor or a data logger, is the way that you can set it up to investigate it. So you definitely need a protractor hanging from the clamp stand, being fixed in a position. You will also need a card to be fixed on the clamp stand, because that's where you can place a reference mark for the equilibrium position. You will need to measure the mass and length. Well, the mass that you place here, basically, and the length of the string using a ruler. This one you can do with the balance. Then you'll move the mouse to the side, just like in the picture, and make sure that the string is taut, so stretched properly. Measure the angle between the string and the vertical using the protractor. So basically, this angle. So this is your protractor here that's fixed. You can use that to get the angle theta from there. And it's advised that you get to that it's less than 10 degrees. Otherwise, the mass won't swing with simple harmonic motion. It will bounce around a lot. So this is suggested to be 10 degrees maximum, so it avoids any conical motion at the same time. And you release the mass. You make sure you position your eye with the reference mark on the card, and then you start the stopwatch when the mass passes in front of it. So as soon as you let it go and you see the mass passing the reference mark, you start the stopwatch. Then you record the time when the mass passes the mark again, when it's moving from the same direction, so after it completed an oscillation. And if you will notice, actually, it's not if, you will notice that for one oscillation only, it actually takes such a short amount of time that your value won't be accurate. So you won't be able to make an accurate measurement. So what you will need to do then is to measure the total time it takes to make, let's say, 10 or 20 oscillations. Ten or 20 oscillations is enough to basically drop your uncertainty in your measurement, and to kind of disperse the human error in terms of using a stopwatch to time how long it will take for 10 or 20 oscillations. You definitely need to record that time as soon as you take it. And since you are measuring how long it takes for, let's say, 20 oscillations, then you, let's just say it took it, I don't know, 5 seconds, then how much is for one oscillation? So what's the period? How long did it take for one oscillation? Then you do, obviously, the division, and you will get the time it took for one oscillation only. To do that, you could do 5 divided by 20, and that will give you how long it was for one oscillation, which is a quarter, 0.25 seconds in this case. Now, like I said, this method ensures that you the timing over a lot of oscillations ensures that human reaction time does not contribute as much to the error, to the uncertainties, as much as one oscillation would only. So yeah, you definitely repeat. You can use this experiment to investigate a different variables each time. So if you change the length of the string, then that would change So, for example, if you increase the length of the spring, the time period will also increase. If you change the weight of the mass, so by, for example, yeah, of that bob. So if you change the weight of the mass at the end of the pendulum, then you can investigate what will happen to the period, which usually might not affect it. And if you change the amount by which you initially move the mass before releasing it, you might notice that that has no effect as well either. So basically the angle. This is pretty much everything that you need to know in terms of what's going on with the experiment. Another little bit that I wanted to mention, actually, you know, the reference line that I mentioned here, sometimes they call that the fiducial marker. And sometimes it could be like a little vertical point hanging, so it doesn't always have to be a line marked there, so it could be in any form. Okay, so we've been through most of this now. I will do these other points in the next lesson of chapter 17.